Right. So thank you so much, everyone, for joining this session again. Today, we are into the second session of Module 2. Module 2 is about wireless LAN physical layer. And we are going to today talk in a little bit more detail about modulation encoding and MIMO Basics. So a lot of you, if you are from the Wi-Fi background, you hear this term called MCS a lot. And what is MCS? Modulation and coding schemes. So what is modulation? What is coding? What are the concepts behind it? We're going to talk about those things in today's session. So before we jump into today's session, let us quickly recap what we talked about in the last session. In the last session was the first session in the physical layer. We talked about the frequency spectrum allocation for Wi-Fi. Wi-Fi has spectrum allocated, uses unlicensed spectrum that is available in the 2.4 gigahertz, 5 gigahertz, and 6 gigahertz band. We talked about how much bandwidth is available in each band, what are the channels that are available, how many non-overlapping channels we have, how do channel bandwidths work, and we talked about all those things. We also touched upon basics of signals. We discussed what is a wave and why does energy propagate from one point to the other point in the form of waves, and how does that happen, how kinetic energy gets transformed into potential energy, how potential energy transforms back into kinetic energy, and it creates a cyclic waveform on which information can be carried. So we talked about that. We talked about the fundamental properties of a periodic signal. We said there is amplitude, which is one of the properties, frequency is one of the properties, phase is one of the properties, and we also talked about how you can vary these properties to actually carry information on top of signals. And we discussed that in detail. And then we also touched upon spread spectrum techniques and the various multiple access techniques that we have in the physical layer, including frequency hopping spread spectrum, which is one of the early versions of spread spectrum technology that was used in Wi-Fi. And then we talked about direct sequence spread spectrum. And then we also touched upon OFDM a little bit. We explained the differences between these methods using examples. So if anyone missed this session, this is on our website already. The video recording is available. The slides are available. You can always go back and watch it. So how do you stay connected? Here is the links and the QR codes to access the course webpage. And you can certainly go and look at all the material there. And you can also register if you have not registered using the registration link. As our moderator has said, there is a WhatsApp group available, although I was told that we reached capacity on the WhatsApp group. So I think we already have like 1,024 participants in the WhatsApp group, which is pretty cool. More than 1,000 people joining that group is pretty awesome. What I found out is that there is a limit there, and so we're trying to figure out how to actually solve the problem. If someone is trying to join the WhatsApp group and not able to join it, then please do send us an email at training@candelatech.com, and then we'll try to get you in somehow. Okay, right. So coming to today's topic, modulation encoding and MIMO basics. So let's talk about modulation a little bit. Like this is a slide from last session. So what is modulation? Just to recap, modulation is the process of varying one or more properties of a waveform to carry information. So what are the properties? We said amplitude is a property, phase is a property, and frequency is a property. These are the properties of a periodic waveform. And by varying these properties, you can actually carry information. So if you're changing frequency, like for example, if you want to send zeros and ones, let's say you want to send a zero, the transmitter, this being the transmitter, will have an agreement with the receiver. So this is the transmitter, this is the receiver. The transmitter and the receiver will have an agreement that we are going to use frequency to carry information, or change the frequencies to carry information. So what that means is the transmitter says, okay, I'm going to now send information at a higher frequency, and that would represent a 1. And if I'm sending information at a lower frequency, that would represent a 0. And that is the agreement between the transmitter and receiver. And if that's how they have agreed upon, then the transmitter will send a signal at lower frequency, and that the receiver will receive that and say, okay, this signal is at lower frequency. That means that information should be a 0. Next, it received the information at higher frequency, then it must be a 1. So that's how the frequency shift keying works, like we mentioned last time. Same thing with amplitude shift keying, where you vary the amplitude. So for example, when I'm speaking at a certain volume, and you can also consider that as the amplitude of the sound waves that are coming out of my mouth. So for example, I can talk to you and say, let's have an agreement that when I speak very loud, that means it's a 1. And when I speak at a very low volume, that means it is 0. And we can come to an agreement between the transmitter and receiver. And if every time I'm speaking at a very high volume, you'll assume that you're receiving a 1. And if I'm speaking at a very low volume, you assume that I'm receiving a 0. So that is an agreement between the transmitter and receiver. And if the information is being sent that way, then it's amplitude shift keying or amplitude modulation. And then same thing with the phase. So if you're changing the phase and not changing the other properties, then it's phase shift keying. So like we discussed last time, one of the things with amplitude shift keying, phase shift keying, and frequency shift keying is that these methods will only change one property at a time. So what that means is if you are shifting frequency, then you can see in this waveform that you're only changing frequency. You're not changing the amplitude. The amplitude of all the waveforms are the same. And you're not changing the phase. The phase is also the same. So you're only changing frequency. So when you're doing amplitude modulation, you're only changing amplitude. So you're sending 0 at a low amplitude, 1 at a high amplitude, but you can see that the frequency of the waveform is the same. It's not changing. Same thing with phase shift. So if you are changing the phase, like you can see when you're sending a 0, you're sending it at a certain phase, and then you're shifting the phase, then you're keeping the amplitude the same and the frequency the same. Right? So these are methods that are what we call as the simpler modulation techniques, which only change one property at a time, and they're not very complex, but at the same time they cannot carry a lot of information, and so you cannot get very high throughput. Now of course we talked about QAM last time, or quadrature amplitude modulation, which is a technique that changes two properties at a time to be able to carry more information. For example, if you change both amplitude and phase at the same time, then you will be able to send more information. For example, you can say I'm going to use a certain amplitude in a certain phase, and in that way you can actually send more bits in one signal or one symbol. How we do that, I'll explain that in the coming slides. But amplitude and phase shift, which is done by QAM, is what we call as a little bit of a higher order modulation rate, which basically uses the spectrum more efficiently, which means that it is able to send more information in the same amount of spectrum, or using the same amount of signals, and hence the spectral efficiency is higher, right, in that method. We'll talk more about it in detail in the coming slides. So if you look at what are the different parameters for these different modulation rates, you can see that QAM, or quadrature amplitude modulation, is the highest complexity. As I said, the complexity is very high, and you can also get very high throughput, highest data rates, but it has the lowest immunity to noise when compared to the other methods here, because it varies multiple things. So then it is actually harder to estimate the right information when there is noise at the receiver. Right? And why is that? I'll explain that in more detail in the coming slides. Okay, so let's start with some basic example here. So if you look at what is used in Wi-Fi, we primarily use phase shift keying, or PSK, and QAM modulation rates. These are the two main modulation types that are used in Wi-Fi technology. And why? Because they are the ones that have the higher data rate, and you can use the medium more efficiently. So let's start with a very simple example of BPSK, or a form of PSK, or phase shift keying, that is the simplest version, or it's also called as binary phase shift keying, which means that this modulation method will only carry one bit per signal or symbol, right? So how does that work? You can see that if there is a waveform, so the transmitter is going to say, I am going to send this signal or waveform with 0 phase shift. And if I'm sending it at 0 phase shift, that represents a bit 0. So if you look at this axis, this represents a 0 degree phase shift, and this represents a 180 degrees phase shift. So if I'm sending information at 0 degrees phase shift, I can say that is bit 0. If I am sending information at or transmitting the signals at 180 degrees phase shift, remember that this waveform, this is one cycle, right? You can see from here to here, this is one cycle. So what does the one cycle mean? It starts from 0 degrees. So this is 0 phase, 90 degrees, 180, 270, and back to 360, which is 0. So it's like one full cycle, right? and once a full cycle is represented by one waveform here. So if you are starting the transmission at this phase, then it is 0 phase. If you're starting it here, then it is 90 degrees phase. If you're starting it here, then 180 degrees phase, and so on. So now if you're starting here, then you're saying you're at 0 degrees phase, they're sending bit 0. Then if you are starting here at this point, then you're sending at 180 degrees phase, and that is a bit 1. Right? So that is how BPSK works. It's basically very binary. You're only sending 1 or a 0, and you have about between 0 and 180 degrees to actually send this information. So this is how it works. If you're sending a 0 and 1, you send the 0 like this, and then you shift the phase by 180 degrees and then send a 1. Now, if the transmitter and the receiver are locked in phase, which means that they have actually a synchronization of phase, then the receiver knows, okay, I just received a symbol at 0 degrees phase, so that must be a 1 or a 0, and then now suddenly I received something at 180 degrees phase shift, so that means I must have received a 1, and that's how the receiver will receive the information. So it's the most simplest form of phase shift keying modulation method. Now you can go a little bit more complex. Then the little bit higher order is QPSK. So QPSK is not sending 1 bit per symbol, it's actually sending 4 or 2 bits, right? So 2 bits would represent 4 combinations. So the 4 combinations to send 2 bits are 00, 01, 10, and 11. So now what is happening here is, again, it's a phase shift key modulation. So the transmitter is saying, if I am sending the signal at 45 degrees phase shift, that must be, let's say, one of the 4 combinations. That could be 00. If I'm sending, say, the signal at 135 degrees phase shift, then that must be a 01. If I'm sending at 255 degrees, then that must be a 10. And if I'm sending at 350 degrees phase shift, that must be a 11. So now you have 4 choices rather than only 2 choices between 0 and 180 degrees. Now you have 0, or in fact, if you start with 45, you have 45, 135, 225, and 315. So they're all each 90 degrees apart in phase. So now between 0 and 360 degrees, you have 4 combinations. And the 4 combinations will give you 2 bits, 00, 01, 10, and 11, 4 combinations. So now if you're sending this waveform will represent a 00. This waveform will represent a 01. This waveform will represent a 10, and this waveform will represent a 11. So not changing frequency, you're not sending anything faster. Remember, one thing to remember here is when you're actually sending information, the speed at which the waves move from the transmitter to receiver, that speed never changes, right? The signals still travel at the speed of light. So the speed at which the signal is being transmitted from here to here does not change. So what changes is how much information you're carrying on that signal. And the more information you carry in the signal, the higher the data rates and the more the throughput. It's a very, it could be confusing sometimes that when you say I'm getting better throughput, you might imagine that the signals are traveling faster. No, they're not traveling any faster. They're just carrying more information, right? And that's how you get better throughput. Now take that same example to a little bit more complex modulation rate, which is 16 QAM. So 16 QAM is basically 16 combinations. Again, 2 to the 4 is 16, so you can send 4 bits of information. So how do you do the 16 QAM? Now you're actually not just doing phase shift, you're also changing the amplitude. So now you get into the QAM space. So QAM, or a quadrature amplitude modulation, is shifting both amplitude and phase. So now you can say, okay, let me have 4 levels of amplitude, level 1, level 2, level 3, level 4. And then I have 4 degrees of phase, equally distributed between 0 and 360 degrees. And that will give me 16 combinations. What that means is, if I am sending a signal at amplitude level 1 and at 45 degrees shift, that must be combination 1. And combination 1, let's say, is 0, 0, 0, 0. Like that, I have 16 combinations, 4 times 4. And these 16 combinations are these 16 combinations, which represent 4 bits. So now on the same signal that you're transmitting before, now instead of carrying 1 bit or 2 bits, you're actually able to carry 4 bits of information. And that's now suddenly going to increase your throughput 4 times in theory when compared to BPSK, right, where it's only carrying 1 bit on a single symbol or a single wave. waveform. So that is 16 QAM. So like this, you can keep going to higher and higher order modulation rates. But there is this important concept we need to understand here. Why can't we always use 16 QAM? If 16 QAM is going to give you 4 times or the throughput when compared to BPSK, why do we even need BPSK? We can always use 16 QAM. So there must be a trade-off, right? So you go to higher order modulation rate, you get better throughput, but you are trading off something. So what is that? That is reliability, right? So there is a throughput to reliability trade-off when it comes to modulation. So just to take a simple example, let us say you are transmitting at using BPSK. So that means that each symbol or each wave can carry only 1 bit, right? So let's say you're sending 0, and this is the waveform you're sending, right? At 0 degrees phase, you're sending this, the transmitter is sending this information. But that information is actually going through what we call as a noisy channel. So for example, let's say this is the transmitter and this is the receiver, and they can see each other. The medium is very clear, there is no noise, and it's a very clean channel. Then the transmitter can transmit, and the receiver will receive exactly what the transmitter is transmitting. It is not going to lose amplitude. There will be some little bit of fading of amplitude, but most of the signal will receive, and it will not be out of phase, and it will receive exactly what's being sent. But that's not how the real world works. In the real world, these two can be very far away from each other, or this could be because behind some obstruction. So which means, or there could be some noise. Someone could have turned on a Bluetooth headset or a cordless phone, and that is causing noise in the frequency channel. And that noise can distort the signal. So let's say this particular transmitter is sending that particular sine wave, the wave at 0 degrees phase. When that signal gets transmitted, propagated through a noisy channel, the receiver might receive the same signal at a phase shift, right? For example, it might receive it at a 45 degrees phase shift. So now somehow the receiver needs to still know that what was transmitted was bit 0, because there are two options, remember, in BPSK. If you're transmitting at 0 degrees phase, then it is a 0. If you're transmitting 180 degrees phase, then it's a 1. So the receiver, when it receives this information, the received information is not at 0 degrees phase and not at 180 degrees phase. So now it is confused. Is this a 0 or is this a 1? Because it's not at 0, it's not at 180. That's the agreement I had with the transmitter. The transmitter clearly told me if I am transmitting at 0 degrees phase, then it's a 0. If I'm transmitting at 180 degrees phase, it's a 1. But what I received is a 45 degrees phase shift. So I'm now confused. I don't know what's going on. And that's what the noisy channel does, because it will distort the signal. So now the receiver has to correctly estimate what was being sent. Now you can see that in the BPSK model, if you put this on the same line and you see the distance between 0 and 180 degrees here on this line here, in this BPSK model. So this is what's transmitted at 0 degrees phase, and what was received as was 45 degrees phase. Now when the receiver looks at this and says, okay, I received at 45 degrees phase, but what I received is much closer to the 0 degrees phase than the 180 degrees phase. So the probability of what was actually sent being a 0 is much higher than what is being sent to be a 1. So the chances of this being a 1 is actually very low, because the distance between here and here is very far, as opposed to distance between here and here, because there is a huge basically distance between 0 and 180 degrees. So now the receiver will say, okay, I can with very high probability estimate that this bit to be 0 and not a 1. So what you can see clearly here is, because of BPSK, even though you're sending less information, in a noisy environment, you can recover the transmitted information with a higher probability, even though the received signal is distorted. So that is where the reliability factor comes in. Now apply the same logic to QPSK. Now you can see that the distance between the points has decreased. Now you have 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So now this represents a 0, 0, this represents a 0, 1, this represents a 1, 0, and this represents a 1, 1. Now if you receive it at 45 degrees phase shift, now you are really confused. We don't know if it is 0, 0 or 0, 1, because the received signal is equidistant from these 2 points. It could be a 0, 0 or it could be a 0. We don't know. We cannot really estimate it correctly. Even if we estimate it, we only have a 50% probability of that being correct. So now the chances of having a bit error is higher because these points in the phases are closer to each other. So now as you go higher order modulation rate, you are doubling and quadrupling your throughput, but you're also basically reducing your chances of correctly recovering the information in a noisy channel. Now all of this does not matter if this doesn't exist. If this channel is not noisy at all and it's a very, very clean channel, then you don't need to worry about any of these things, right? Then you can go very high modulation rate. But that's not what the real world is. The real world is a noisy channel. So based on how much noise you have in the channel, you have to figure out what modulation rate to use. The more the noise, the less reliable the environment is, the more error prone it is. And so you have to drop down to a lower, more reliable modulation method, even though you lose throughput. So you have to trade off throughput for reliability because you want to maintain a connection. So that's basically the fundamental idea and concept. Now you apply the same thing to 8 PSK. Here you have 8 combinations, which are 3 bits. Now these points are even more closer. Now it's even more confusing, right? And the chances of you actually correctly recovering the information when there is noise is even lower. Right? So that means that it's more error prone. So that is basically the idea, the throughput reliability trade-off when it comes to the modulation rates that we are using. Okay, so what are the other modulation rates, higher order modulation rates that are being used? So we talked about BPSK, right? Either a 0 or 1 bit per symbol, either a 0 or a 1 on a single waveform. Now, if you double that, then you have QPSK. It's 2 bits per symbol, and then you can go 4 bits per symbol, and then you can go 6 bits per symbol, which is 64 QAM, right? 64 QAM is 64 combinations across the amplitudes and phase. So basically you have 8 levels of amplitude and 8 levels of phase, and 8 times 8 gives you 64 combinations. So now you can see how close these points are getting to each other. You can see that here, from here to here, there is this huge gap, and so but from here to here there is very little gap. So the margin for error in case of noise is actually very, very low as you go to the higher order modulation rates. Now you can send 6 times information, but it's more error prone. Now you apply that to 256 QAM. Now you have 256 combinations of amplitude and phase in the same section. That's going to give you 8 bits per symbol. And then we talked about 256 QAM is used in the early standards, and then it came to 1024 QAM. And now with Wi-Fi 7, we have 4096 QAM, where you have 4096 possible combinations of amplitude and phase that would be transmitted in a signal. So that's so granular, which means that the probability of error and the probability of the receiver receiving the information in a wrong way is very, very high. And this is one of the reasons why when you're using a very high order modulation rate, you need to be in close proximity between the transmitter and receiver. You need to have very good RF channel and very low noise, right? And only then you can transmit successfully at these rates. So those are some of the rates that are used to achieve the different amount of throughput. Now, what is an MCS table? What are MCS rates and all of that? We'll talk about that in more detail in the next session. These are only the fundamentals that I'm talking about here. So you might have also heard, so those who are in the wireless communications and Wi-Fi space, you might have also heard this term called EVM, or it's also called error vector magnitude. So error vector magnitude is, in very simple terms, what it is it's basically the distance between the desired point. For example, if I'm sending a 1-1 and 1-1 is on the IQ axis, it's at this point. Right? This is where it should be, but the received signal was received at this point because it is distorted in phase and amplitude. So the amplitude changed because of the noise of the received signal, and the phase changed because of the noise. So both amplitude and phase changed, and because of that, the received signal point is here when it should have been here on this IQ axis. So the distance between what is received and what should have been received, this is called the error vector magnitude, or the amount of error you have on the receiver side. And normally error vector magnitude, or EVM, is represented in percentages. It's also represented in dB. Now there are formulas to convert dB to percentages and so on. Now, as I always keep saying, I want to avoid formulas and equations in this. So I didn't really put any equations or formulas. But if anyone who is listening is interested in formulas and equations, and if you'd like, please post that in the chat window for others to look into. So the error vector magnitude is nothing but a measure of the quality of the performance of the digital transmitter or receiver, right? The signal sender, it's looking at the difference between what was received and what should have been received. And if you look at this particular table, BPSK is the simplest and the lowest modulation rate, simplest modulation rate. For that, you can get away with having very low EVM. So for example, you can have a very high gap between what was received and what should have been received, and you can still recover the information because BPSK has this huge margin of error. But as you increase your modulation rates, you go from BPSK to QPSK to 16 QAM, 64 QAM to 6 QAM, you can see that the EVM it becomes you need lesser and lesser error margin, right? So the EVM gets lower and lower and lower, and so you have lesser and lesser error margin when it comes to the higher order modulation rates, which is what I was talking about in the previous slide. Another thing we want to talk about is I'm trying to cover the various terms that you normally hear in the physical layer. So one of the other things is the characteristics is what we call as RF power or transmit power and its units. So that's we're going to talk about that in this slide. So RF signal strength or power can be measured normally in watts in the absolute value, and basically it is measured using the amplitude of the signal. So the amplitude of the signal is nothing but the distance between the highest point of the signal and the lowest point of the signal, right? So that can be measured in watts. So for example, what is amplitude? Again, as I mentioned before, if you take a sound wave, I am talking right now to all of you and I am transmitting it at a certain volume, right? And so there is an amplitude for the sound waves that are being generated from my mouth. Now, if I speak at a lower volume, the sound waves that are being generated would have lower amplitude. So me as a transmitter of sound waves has the ability to increase or decrease the amplitude of the waves, and I can measure that. If there is a machine that is measuring the volume that is coming out of my mouth, and it can measure that in decibels and report that in decibels. Similarly, RF signals are also measured in watts and decibels. So this is basically a conversion table. So decibel is a logarithmic scale. So you can look at this data and say, okay, what does watts correspond to decibels? A lot of the times in the Wi-Fi world, we say, okay, transmit power is 20 dBm or 10 dBm or 0 dBm. So that is a decibel unit measure of power, and that can be converted into watts or milliwatts by using a simple calculation and simple formula. Again, those of you who like formulas can certainly post that formula in the group for others to see. And then what are the things about decibels from a relative point of view? So absolute power is just here. You measure decibels have an absolute power notation and a relative power notation also, right? So the absolute power is here. So 100 watts means 50 dBm, 10 watts means 40 dBm. Normally a Wi-Fi transmitter transmits around 100 milliwatts approximately, so that's about 20 dBm, right? So that's the absolute power measurement. But relatively speaking, there is this unit called dB. For example, if I reduce my transmit power by half, so let's say I'm transmitting at let's say 100 milliwatts, and now I drop it to 50 milliwatts. I reduce it by half, and if you convert that to dB, that is 3 dB. So every 3 dB of increase of power represents doubling of the power. Every 3 dB decreasing of power represents making the power reducing the power by half, right? So that's how the calculations work. So now the transmit power is measured in dBm, and the difference between the path loss, for example. What is a path loss? Path loss is the difference between the transmit power on the transmitter and the receive power on the receiver, and that the difference is called the path loss. The path loss, which is the relative power, is also measured in dB, right? So transmit power is measured in dB, the absolute power, and the relative power is also measured in dB. So to take a simple example, let's say the transmitter is transmitting at 500 milliwatts, which converts to 27 dBm, right? And the receiver received the signal at some other dBm, minus 29 dBm. So now what is the path loss? The path loss is difference between this and this. So that's 27 minus 29. That is 56 dB of path loss. So as the receiver goes farther and farther away from the transmitter, there is more path loss. And we'll talk more about the path loss in the next few slides. So these are some of the things that we normally hear in the Wi-Fi world, decibels, dBm, dB, and so on. So then the other term that you normally hear all the time is what we call as RSSI, or received signal strength indication, RSSI. Yeah, RSSI is nothing but the measured power at the receiver. For example, this guy is transmitting, and let's say he transmitted at 100 milliwatts or 20 dBm, and this guy is receiving it at, let's say, 50 milliwatts, or half of that power, right? So and so that is its RSSI. Whatever it's receiving it as, that is the RSSI, and the RSSI is also measured in dBm. So normal Wi-Fi connection, you can see the connection health here. Normally the AP transmits at 20 dBm, positive 20 dBm power, and let's assume that there is a 30, 40, 50 dBm loss over the air, as you are at the client is different distances from the access point. So let's assume that you're receiving the signal at around minus 30 dBm, and you can check this out in your phone when you go and actually open a Wi-Fi, some form of Wi-Fi scanner app, and you're scanning the different Wi-Fi access points. It will tell you what is the signal strength you're seeing, or RSSI you're seeing from various access points, and that is normally measured in dBm. So if you're seeing around minus 30, minus 40 dBm, then that is considered as a very good signal, right? And if you go down, like mine, this is a negative number, so minus 60 is okay signal, and then if you're going all the way up to minus 70, minus 80, minus 90 dBm, then the signal quality is decreasing a lot. And then at some point, depending upon how good your receiver is, at a certain RSSI value, you will lose connectivity and you'll disconnect, because you cannot hear the transmitter anymore, right? And you disconnect. So that is what is normally referred to as RSSI. Another very important term that is used in the Wi-Fi world is signal to noise ratio, right? So what is signal to noise ratio? In very simple terms, it is the comparison, or the amount of signal when compared to the amount of noise in this particular location. So just to give you a very, very simple example, let us say I am talking to you on this call, and I am speaking at a certain volume, a certain amount of energy is coming out of my mouth, and that you can consider as signal. So what is signal? Signal is nothing but the useful information. So whatever I'm saying to all of you on this call, you consider that as useful information. That is the information that you as a receiver want to receive and process. So you want to hear to the words that are coming out of my mouth, process them, right? So that the words that are coming out of my mouth can be considered as the signal. Now, if there is no interference at all, then it's only signal. There is no noise. But in the real world, there is noise. For example, in this room, there is an air conditioner turned on. Okay, that is creating a certain level of noise. I might not be able to hear it very well, but it is actually creating some noise. I have the fan turned on, and the fan is creating a certain amount of noise. And there is this little bit of a buzz coming out of my laptop, and that is creating a certain amount of noise. As I speak with you, and my information is being transmitted from here to wherever you are in this world, and as it goes through various hops in the network, there could be some other disturbance or noise. So these are all the factors that contribute to the noise in the medium. And the more the noise that you have in the medium, the higher the noise floor when compared to the signal. So if you want to maintain a good signal to noise ratio, which means the signal is always better than the noise, then there are two options. Either you reduce the noise floor, which means you have very low noise. For example, when I set up this call, what do? I turn off the fan, because I don't want the fan to create some noise here. I don't know how clearly you can hear me if I have a fan turned on. So I turn off the noise. So I'm trying to reduce the noise floor. Or I try to do something else. I try to keep the door closed so that no one is disturbing me. I don't hear any external voices. So I'm trying to reduce the noise floor, right? Because I know my signal level is constant. I cannot speak any louder than this. Or the other option is, if I know that there is going to be a lot of noise here, then I can somehow increase the signal. For example, I can use a megaphone or a microphone. For example, if you are in a big event somewhere and everyone is talking, so the noise floor is very high. So your voice cannot go any higher. So what do? You take a megaphone or you take a microphone and then you speak into it. And now you're raising the signal with respect to the noise floor. Now all the receivers can hear you again, even though there is a lot of noise, because you've raised the signal power, right? So to have a high SNR or signal to noise ratio, either you increase the signal or you reduce the noise. Either way, the ratio of signal to noise should always be higher, right? So that is the idea of having good signal to noise ratio. Again, if you take this example of this transmitter and receiver, when he's transmitting and he's receiving, they are very close to each other. So the amount of loss of the signal over the air is very less. There are no obstructions. There is no noise. So that means that this guy will receive the signal at a very good signal to noise ratio. Now someone turns on a Bluetooth headset right here in the middle and transmits in the same frequency. Now you raise the noise floor. Now this communication is obstructed. Now this guy has to raise his signal, right? Or he has to use a modulation rate that is able to tolerate a lesser signal to noise ratio. That's the other concept we have. For example, in the case of Wi-Fi, there is only a maximum transmit power you can transmit at. Okay, so you cannot go any higher than that. So you cannot use a megaphone because the standard has restrictions on the amount of transmit power. 100 milliwatts or 1 watt that is the maximum power you're allowed to transmit from an access point. So that cannot go any higher, right? So now your only option is I cannot increase the signal anymore. So there are only two options. Either I somehow try to reduce the noise floor, or I try to use a modulation method that can tolerate a lesser signal to noise ratio, right? So that means that as this device is going far away from the access point, when I cannot increase the signal and when I know that the noise is getting increased, then the signal to noise ratio is dropping. So now what I do is, instead of using 16 QAM, which needs a higher signal to noise ratio, because remember that it has lower margin for error, which means that it needs a better signal to noise ratio, right? So I say, okay, instead of transmitting a 16 QAM, I will give up some throughput and I'll go down to BPSK, right? And this is what's called rate adaptation or rate scaling in Wi-Fi. So as you can see here, BPSK, which is the lowest modulation rate, can live with a very low SNR. But as you go to the higher modulation rates, you need very high SNR. So what is this 17.99 or almost 18? What this is saying is the signal to noise ratio is 17 dB. So if you do all the calculations back, the signal has to be at so many times better power level than the noise floor for you to be able to communicate using this modulation rate. So if you are communicating at this modulation rate and your signal to noise ratio is not at least this much, then you will see errors on the receiver, and the receiver will not be able to decode what you're saying, right? So I'll give you another simple example. For example, I am talking to you at a certain pace. I'm talking to you slowly, right? So I am saying, hello, how are you doing? So what am I doing? Within that certain amount of time, I'm only able to transmit 4 or 5 words, okay? But you can clearly hear me because I'm transmitting only those 4 or 5 words. So let's say the channel between you and me is very clean. There is no interference. And you can very clearly hear me. I'm asking you, am I audible? Can you hear me? Is my voice clear? And when you say your voice is very clear, now I am more confident. So now I'm going to say, okay, I'm going to speak really fast. I'm going to talk about this. So I'm going to speak much faster now because I now know that the channel quality is very good. That means that you're able to decode my information faster. So now with the same amount of time, instead of speaking 4 words, I'm going to speak 10 words. So I'm increasing my throughput, right? Because I'm relying on the receiver's ability to receive it well. But let's say the channel gets bad between you and me, and then you say, oh, hold on, wait a minute. I can't understand what you're saying. You're speaking too fast. There is so much noise here. I can't understand what you're saying. So that feedback you'll give me. And when you give me the feedback, I'll say, fine. So now there is some noise here. I cannot speak that fast anymore. So I need to reduce the speed. And I'm going to speak much slower and in a much more distinct way, right? So now I'm reducing my throughput, but I am increasing the reliability of my communication. It's the same exact concept that Wi-Fi uses for what we call as rate adaptation, where you adapt to the channel conditions and use the right rate of coding to be able to successfully communicate on that particular channel at that particular time, right? So that's called rate adaptation. We'll talk more about that in the coming sections. Okay, so we talked about modulation, which is good, but a lot of you who are in the Wi-Fi world might have heard this term called MCS, or modulation and coding scheme. So most of the data rates that we are getting in Wi-Fi, in the next session we're going to talk about MCS tables and all of that. So it is not just modulation that you're changing to get higher data rates, you're also changing something called as coding. So what is this coding, right? We'll talk a little bit about that here. So coding, if you look at how digital the transmission and reception works, you're trying to send data from the transmitter, and that data is source coded. So you apply source coding. We'll talk about what that means. And then after that, you do channel coding, and then you do modulation. You apply different types of modulation rates, QPSK, PSK, QAM, and so on. And then you take the digital bits and convert them to analog, and then that information goes over the RS circuitry. It gets up converted into, remember we talked about carrier frequency, where you need to take the information signal and put it on the carrier signal. So the RF circuitry does all that up conversion, and then the signals are transmitted, and then they go out the wireless channel, and on the receive side, exact opposite happens. The RF circuit receives the information signal, I mean the carrier signal, and then it basically removes the carrier signal and gets the information signal. It does the analog to digital conversion. Then it does the demodulation. Remember, if you use QAM modulation, you have to demodulate it. And then you'll do channel decoding and source decoding. And that's where you end up with the data on the receive side. So there's this whole process that is happening. So now what are these things? Source coding and channel coding. Right? Source coding is nothing but like your, when you zip a file, right? You take a certain amount of bits and then you zip it and you make it lesser, you compress it, right? And the compression algorithms are designed in such a way that when you decompress that information, you will be able to fully recover without any probability of error. You will be able to fully recover the original information. So source coding is nothing but taking your source data and compressing it to some extent. Now, once that is done, then that information, again, which is ones and zeros, will be channel coded. So channel coding is exact opposite of source coding. It's actually adding redundancy. Instead of compressing it, it's adding redundancy. So why is it adding redundancy? Because again, remember that the channel may not be ideal between these two devices, between the transmitter and receiver. If the channel is not ideal, then what the transmitter does is it adds some redundancy so that the receiver can correctly detect the transmitted information, even though that information is errored. So that's called as forward error correction. So we are trying to correct the error in a forward way even before we transmit. As we are transmitting, we are trying to put some logic in there that would correct the errors in case the information was received with error. So that's called channel coding. In very simple terms, if you heard a term called 3/4 code, right? Channel code. So what that means is, for every 3 bits of information, you are actually transmitting 4 bits. So that means that you have an extra bit, which is the redundant bit, right? And so that means that there is added 25% information redundancy. So the more redundancy you have, the more reliable your communication is. But again, the lesser your throughput, because you're adding more overhead, right? So again, it's a trade-off between throughput and reliability here as well. So we don't have time to go into this in more detail, but if you look at this example, let's say you're sending these bits as data, you can channel code those bits by using a larger number of bits. So instead of sending 3 bits, here you are sending about 12 bits of information, right? So to represent these 3 bits. Now, when you send these bits, if you receive, what you received is something different than what's being transmitted because of errors on the link, because of the signal quality being bad, you receive this information. So now what you do is you look at the received information, and then you check the lookup table and see what is the closest match. So for example, this sequence of bits are 4 bits different from this one. This sequence of bits are 7 bits different from this one. But this sequence of bits here is the best match because it's only 2 bits different from what's received data. So now when you look up in this table and say, I received this, but this is closest to this information, which means that I can estimate that what I received is actually this, which corresponds to 011. So now, even though there are errors, bit errors on the link, you have, using this estimation method, currently recovered the actual transmitted information. So you've added redundancy, but you've increased reliability, right? So that's how basics of channel. I put in some references here, which will give you more information about this as you go through that. Now, some of you, again, who come from the Wi-Fi world might have seen this these kinds of data sheets which talk about the RF performance cable of an access point. So here you are showing how good the receiver of the access point is by looking at the receiver sensitivity numbers. So here you can see saying that when the transmitter, let's say in this case the phone is a transmitter and the access point is the receiver, and he is transmitting at a certain modulation rate, 1 Mbps, let's say 1 Mbps corresponds to BPSK, then this receiver on this access point can successfully receive that information that is transmitted at that modulation rate all the way up to -97 dBm RSSI. So at very low RSSI also, it can recover that information. That's what this table is saying, right? On the other hand, let's say you're using something at the bottom of the table here, MCS11. MCS11 is the highest of it's the 1024 QAM, where it's trying to send 12 bits per symbol. That is a lot of information, a lot of throughput. But if this guy is transmitting in MCS11, then the receiver can receive their information only up to -53 dBm RSSI. So that means that if the RSSI receive signal goes below -53, then it cannot decode the information anymore, and it will start losing the information. So that's what this receiver sensitivity table. Next time you actually purchase an access point, you can actually look at this in the datasheet. This information is taken from, I believe, the Aruba access point datasheet, and this is telling you how good the receiver and how sensitive the receiver is in receiving the different types of modulation rates that are being transmitted by the transmitter. So it's some interesting information if you didn't understand what this is before, hopefully you can understand better now. The same concept here. This is basically what we call as a receiver sensitivity test, where we are actually running what we call as a throughput test at different modulation and coding schemes. So for example, if you're transmitting at MCS9, so the red line here is MCS9, and MCS9 corresponds to 256 QAM, a very high modulation rate, and 5x6 code, which means that for every 5 bits, you're transmitting 6 bits. There's only a very little redundancy here, right? So this combination, 256 QAM and 5x6 coding, gives you MCS9. So this is the one that gives you the highest throughput of all these combinations, and hence you're getting very high throughput. But what you can see is the RSSI is very low. So which means that the receiver, if it's receiving the signal below -65 dBm, then the throughput goes to 0. You'll see very high bit error. So that's the reason why, even though throughput is very high at good signal, as the signal levels goes down at the receiver, the higher modulation rates cannot keep up, and then they will disconnect. But as you go into the lower modulation rates, so for example MCS0, which is BPSK, 1/2 coding, you can see the throughput is very low because we're carrying lesser bits per symbol, but it can go very far, all the way here up to -90 dBm. So again, you can see on this plot the trade-off between throughput and the reliability of the communication. If you have very little information to send, let's say you're sending like 1 megabit per second, very little, like you're an IoT device and you're sending a very small amount of information from the transmitter receiver, then throughput is not your problem. You're not sending a video file, you're not trying to stream 8K or 8K video or anything. So throughput is not your problem. Reliability is your problem, right? So what you would do, you would transmit at a very low modulation rate. This is one of the reasons why a lot of the IoT devices that are used in the market actually don't use higher modulation rates, because they don't need to. They don't need the throughput. They only need the reliability. So they only use very, very low modulation rates. The last thing that we want to talk about here is OFDM, and yeah, we have a little bit of time to talk about it. So OFDM is, we touched upon this last time. So OFDM is one of the primary, basically multiple access methods that are used in Wi-Fi. We of course have OFDMA, which we'll talk about in the later sessions. But at a basic level, as I said last time, OFDM uses this concept of subcarriers, which takes the channel bandwidth. So for example, if you're using .11a, or .11g. Let's say you have a 20 megahertz wide channel in the 5 gigahertz band. So you see that there's a 20 megahertz wide channel. That 20 megahertz is broken down into smaller chunks, sets of frequencies, which called as subcarriers. So we break it down into 52 subcarriers here, and each subcarrier is around 300 and 312 kilohertz wide, right? So of this 20 megahertz, you have about 16.6 megahertz that's actually being used. So when you have these 52 subcarriers, you can see in this picture, some of these subcarriers are what we call as pilot subcarriers. These are used to carry metadata or information about the channel and things like that, and they're not carrying the actual data, right? These are only these are the red ones here are the data subcarriers. The blue ones are the pilot subcarriers. The pilot subcarriers are nothing but they are actually having information about the RF channel and things like that will help in improving the reliability of the communication. They're not actually carrying any data. So these 48 subcarriers would now send information, which is again modulated using various methods. So for example, these data subcarriers could be using BPSK or QPSK or 16 QAM or 64 QAM. The higher the modulation rate they use, the more throughput they'll get, the less the reliability. And then there is a signal field in the OFDM burst. The signal field will actually tell the receiver. So in the signal field, we're saying that what modulation rate are we going to use. That information is mentioned in the signal field, right? And the signal field itself is actually transmitted at a very low modulation rate so that the receiver can successfully receive it, right? Once the receiver receives the signal field, in the signal field there will be the information where all the data subcarriers that are about to follow would be using a certain modulation rate, and then now the receiver knows that, okay, I need to expect the data subcarriers to be modulated using BPSK or QPSK, and then it would do the right demodulation to recover the information, right? So that's just a kind of a high level information about the OFDM. Of course, there's a lot more detail. There's so much more complexity with OFDM. I put in some references here. Someone, if you are more interested, you can study more about this OFDM. Okay, so we need to talk a little bit about, I think this is probably the last slide for today. This is another very important concept that we hear about. It's called multipath. Again, in the Wi-Fi world, especially in an indoor environment like Wi-Fi. Wi-Fi is used mostly in indoor environment. There is this concept called multipath. So what is multipath? Multipath is nothing but the receiver receiving the information from the transmitter in multiple paths, right? Again, if you take this example, let's say he is the transmitter, he is the receiver, and he is transmitting signals from here to here. If they're very close, there is a direct line of sight. There's a direct path between here and here. So the transmitter and the receiver is here, there's a direct path. So the receiver is receiving from the direct path. But remember that the signals that are being transmitted are actually going in all directions because these antennas are omnidirectional antennas. So signals are being propagated in all directions. Remember the example where you drop a stone in the water and then the signals, the waves carry all directions. Similarly, this access point is transmitting in all directions, which means that the signal that is coming out of here is actually going and hitting the wall in front of me and then reflecting from the wall, and then it's coming back to the receiver, right? So there is one path that is going directly from here to here, and then there is another path that is going through a reflection. Now, when it is reflecting from a wall, based on the properties of that surface, that signal could be absorbed a little bit, which means that it will lose some energy, or it could be distorted a little bit, which means that it will be shifted in phase. So there are multiple copies that the receiver is doing. One is a direct copy, which is coming straight without any or without very minimal loss in power. So that is this. So if you look at the time domain, x-axis is time. So one of the copies that is received from the direct path is the one that is received first, because from here to here, this is the shortest distance. So this copy is received at the highest signal at the fastest speed. But then there is a reflected path that is now received at a little bit slower speed, a little bit off in time, and lower in energy, and possibly also shifted in phase based on the properties of the reflecting surface, right? So now the received signal will receive multiple copies. Receiver will receive multiple copies, some distorted in reduced in amplitude because of path loss, some distorted in phase, and so on. So that's what's called multipath. And there is this concept called delay spread. The delay spread is nothing but the distance in time between the first received copy of the signal and the last received copy of the signal. So the difference between these two is called the delay spread. And then there is this concept of fading. So a lot of you have heard of the concept of fading. So fading is nothing but the loss of energy between here and here. So very simple terms, I'm speaking. As I'm speaking, let's say you are 10 feet away from me. The sound waves will get faded over a period of time. When you're 10 feet from me, you will hear at a certain volume. When you're at 20 feet from me, you'll hear at a certain volume, and so on. Right? Now, if there are reflecting surfaces, you'll have resounds, you'll have Doppler effects, you'll have all kinds of other things. And so fading has many types. There is just flat fading. There is just fading because of normal path loss. There is fading because of multipath. There is fading because of delay spread. There is fading because of frequency variation that causes Doppler spread. There are so many different ways in which signals will fade. But fundamentally, the idea is the transmitter is sending energy and the receiver is receiving something lesser than what is being transmitted. And the difference between what is transmitted and what is received is what is the fading part, right? Or the path loss part. So there are many different types of fading. I don't want to get into all these details because we don't have time, but that is another point that most of you know about. Now, of course, the last, I didn't realize that there was one more slide. So one more slide here is about MIMO. So I'll talk about MIMO in about 1 minute here, but then maybe we'll discuss more in the next session. So MIMO is nothing but a multiple input, multiple output, right? So for example, this transmitter, let's say it has one radio chain or one set of transmitter receiver components. It's called as a radio chain, and one receiver on the receive side. Then there is one transmitter, one receiver, and that is single input, single output SISO. But if there are multiple radio chains transmitting and multiple radio chains receiving, right, then it's called MIMO, or multiple input, multiple output, right? So we'll talk more detail about it in the next session. And there is also this concept called spatial stream. Spatial stream is nothing but a stream of information. So for example, if you're doing MIMO, multiple transmitters, multiple receivers, and you're only sending one stream of information between the transmitter and receiver, then the same information is copies of that is sent across all the transmitters and received across all the receivers. This is called spatial diversity, right? This is not increasing the throughput because it's the same data stream being sent, but it is increasing the reliability. Because you have more diversity, the chances of you being affected by multipath are lower. The chances of the receiver receiving the information better is going to be very high. But on the other hand, you have something called as MIMO with spatial multiplexing, where each transmitter, each radio chain will send multiple sets of information in parallel. And so which means that now you're doubling, tripling your throughput. The more antennas you have, the more throughput you get, right? And so now you're doubling, tripling your throughput, and you're using this concept of spatial multiplexing. Right? Again, I had to rush through this because of lack of time, but maybe I'll explain this in more detail in the coming session. So here are some references. Again, I only picked up some references here, but if you Google for this, you'll find lots of really good information online. And certainly, if there are any questions, we are happy to discuss this in more detail on the WhatsApp channel and other methods. So thank you so much for your time.